All righty. The mask off. Nobody's in here. I don't need that anymore. Let's get the chair out of the way. All right, so this video is going to be a quick 5 problems. Name that tune. In other words, I'm going to give you the graph and you're going to see if you can describe it symbolically. And I'll show you a little shortcut from a textbook method that I think is worth mentioning. All right, so what we have here is we have our linear graphs, our quadratic graphs, our cubic graphs, just the basic graphs. And I think we can learn a little something about the behavior of these graphs by just looking at them. So exponents to the 1, right? One-dimensional pictures. I don't know. Yeah, I guess one-dimensional pictures change signs at their roots. Y equals X goes from negative to positive. Y equals negative X goes from positive to negative. X squared, on the other hand, doesn't change signs at 0, right? Doesn't matter if you square a negative or a positive, you get a positive. And in this situation, you do the positive number and then subtract. So you get double negatives. X cubed, an odd exponent, appears to have a change of signs at its root. Positive X cubed goes from negative to positive, negative X cubed goes from positive to negative. And I suppose I should put X to the 4th up here. I'll just do positive X to the 4th. And I guess you can see that that does not change signs. Oh, and that happens to be even. This one didn't change signs. That exponent was even. This one did change signs, and that exponent's odd. So it looks like where something doesn't change signs, we have an even exponent. So if I wanted to write this function with the knowledge that I have right now, I would say that a statement like X plus 3 highlights the number -3. And if I square it, I might get a root that looks like this. Whereas over here, which one does, oh, this looks kind of linear. So I think that's probably X minus 2. And the textbook says, how do you solve for A? Well, you write the Y value 50, you put A there, and you put the number in and you divide. Well, let's do it one less easy step. I know I'm going to use this number and I want to get that out. That in our class, that should sound like a familiar refrain, as in, I get this number, I don't want it, I get rid of it and write this one. So I want the number 50. There it is. I'm almost done. All I have to do is plug 3 in and use it. Well, 3 minus 2 is 1. 3 plus 3 is 6. 6 squared is 36. That's not 50. So I want to get rid of this number and actually bring that one in. That's the one I want to get rid of. And there's a great operation that does that division. That's that graph. All right. And so we're going to do 4 more now. You're going to pause the video. You're going to try it yourself. And I'm just going to do all 4 so that this video is only 10 minutes long. So what do I see here? I see -2 gets me a 0. That looks like a cubic root. So I'm going to write X plus 2 to the 3rd because it changes sign. So it's got to be odd. And it's not a clean cut. I don't know how to describe that, but we will look at in our class why this has that behavior. But right now, we're just trying to get a right answer. So let's make some room for ourselves. Oh, that looks like a quadratic root. This one looks like a linear root. And I know if I use a 0, I'm supposed to get 5 out. So I'm going to put the 5 right there right now. So I'm going to put a 0 in. So that's 8. That's 1. That's -4. That's -32. I don't want that number. I'm going to get rid of that number right now. Boom, it's gone. I want 5. And if you had this situation, hopefully you would take the negative and move it into the numerator because it reads better. All right, moving right along. Naming this tune. I think you can see that well. All right, so what do I see here? I see a linear root. If I put -2 in, yeah, I get 0 out. I see another linear root. I see another linear root. And I see another linear root. Of course, when I put 0 in, I want 9 this time. Right now I have 2 times -1 times -4 times -6, right? If I put a 0 in, right? 0 minus -6. That appears to be minus, let's see, it's a minus number, so 8 times 6, 48. I don't want that. I don't want minus 48. How can I turn that into a 9? Geez, I think I have to multiply it by something. You know what I'll multiply it by first? That. Oh yeah, that cancels. So I guess when you put that in, you don't want that number. You want that number. And just like the last problem, move the negative into the numerator. It reads better. Okay, we got another one here. And at the end, we'll talk a little bit about increasing and decreasing and so on and so forth. All right, so minus 50 looks like a quadratic root. X plus 5 squared. That looks like a quadratic root. X squared. I'm going to put the x squared there. What do you get if you put a 0 in? 0 times anything is 0. Yeah, so that seems to work. 3 gets us a 0, and that looks like a linear root, right? And I'm going to put a 4 in, and I want a -10. So why don't I put the -10 here, and whatever the 4 gets me, I'll cancel it out of the problem. So 16, 4 plus 5, 9, 81. Oh, darn it. 4 minus 3 is 1. Oh, I caught a break at the end. So 16 times 81 is 810 plus 6 and 48. So 810. I got to do it the old-fashioned way. It's too late in the day for me to have trouble here. So 48. Yeah, so I could have done that. 486. Okay. So where was I over here? Yeah, so 486. All right. So 6, 9, 12. I don't want that number. That's not this number. So let me divide it out of the problem. 1296. I suppose if you put this into Desmos as a y equals, I'll bet you get that graph and it goes through all the coordinates we just named. All right, one last one. And this is the one that's really helpful in solving so many Algebra 1, Algebra 2 problems and beyond. All right, is recognizing that we could have written this graph as x times x minus 4, right? 2 linear roots. And now when I put in a -2, -2, that's a -6, that's a -2, that's 12. I don't want 12. I did want 12. Huh. So it worked just the way I did it. Okay, so that was, no need to write that. That was actually this graph. Okay, that was accidental on my part. If I made it 13, why don't I do that? If I made it 13, then I could come back. I don't want 12, I want 13. And that would have been the graph you're looking at now. So what are some of the other characteristics that we learn? When is this function increasing? When is it decreasing? Well, it sure looks like that this vertex is centered between 0 and 4. So that x is a 2. All right, so when is this function decreasing? You answer that question by putting your finger on the graph and following it. Oh, my hand's going down. That must mean all the y values are going down. So it looks like it's decreasing for x values less than 2. And then when I get to 2, it's 0. Well, it's not 0, it's what? Well, I guess we could plug it in and find out. 2 times -2 is -4. -4 goes into 12, -3. So 13 over -3. So the -13 over 3 is actually the y value. So that's the minimum value. Nothing's getting smaller in this function than that y value. You won't get anything smaller than that unless I made a careless error over here. So we don't talk about increasing and decreasing with the y values. We talk about it with the x. So this function is increasing for all x values greater than 2. So when I go to 3, 4, 5, 6, my y values are increasing. And I think that's a discussion that you're having as well. All right, so I'm going to upload this and post it. And hopefully you look at it and learn something from it. Okay. Moment here. Sit down. The old guy's tired. I'm going to end the meeting, which isn't a meeting. I'm going to end it anyway.